Even the original function can tell us something when we do a sign analysis on it. Notice to the right of 0, we're plugging in something positive for x, but because of that -2, the numerator is negative. The denominator, of course, is always positive, so this should be negative in this interval to the right. If we're to the left of 0, then our x value is negative, which makes our numerator positive. Over a positive numerator, the whole thing is positive, and so we'll indicate that as well. Now, graphically, what does this mean? Well, if our original function is outputting values that are negative, we must be below the x-axis. Remember, the output here is the y-coordinate. And likewise, if that y-coordinate is positive, we must be above the x-axis. Now, before we move on to the next bit of analysis, let me draw your attention to one more thing. Notice here we said the function was increasing, and then decreasing, and then increasing again. The fact that our function was going up and then coming down right here at -1, where the derivative exists, recall we have a horizontal tangent, tells us that at -1 we must have a local maximum. So let's indicate that. This is confirmed by looking at the second derivative, which is negative, and thus indicates the graph is concave down. A graph that is concave down, where the first derivative is 0, does indeed produce a local maximum. Something similar happens here at x equals 1. Our function is going down and then rising. Given that the derivative exists there, again, recall the horizontal tangent, we must be looking at a local minimum. So let's indicate that. And again, this is confirmed as well by the second derivative, which is positive, indicating the graph is concave up. Again, being concave up at a place where you have a horizontal tangent suggests you have a local minimum. Now we certainly want to know where exactly the function is at each of these interesting x values. So to that end, we need to find the y values that go with them. So let's create a little t-chart with those x values listed, and then to find the y values, well, how do we find y values given x values? We use the original function. We simply plug those values in here for x, and out pops y. So doing that for each of these 5 values, we get these. And we'll want to graph each one of these points, 0, 0, -1, 1, 1, -1, and so on our graph. And we'll do that in a second, but there's one more piece that we need to look at, and that is the end behavior of this function. By end behavior, I mean, what is this function doing as x gets very, very large when we are on the right end, and when x gets very, very negative when we're on the left end? Of course, in the terms of limits, we're simply talking about the limit as x approaches infinity, hence the right side of our expression, and the limit as x approaches negative infinity, the left side here of our expression. Of course, returning to this expression, notice the degree of the bottom is larger than the degree of the top, and we're talking about a rational function here, the quotient of 2 polynomials, and as such, as x approaches infinity or negative infinity, this x squared term is a very dominant term in comparison to this simple x, or certainly in comparison to this 1. So the denominator of your fraction is growing quite large, quite rapidly, in comparison to your numerator, and thus the entire fraction is going to 0. So both of these limits, and we could justify this more rigorously, say by dividing both the numerator and denominator by x squared in both limits, we can tell, though, that the limit in both cases is 0. This tells us that our graph must have a horizontal asymptote on the far right that is 0 high, and on the far left that is also 0 high. In other words, we have a horizontal asymptote that consists of simply the x-axis on both sides. We are now finally in a position to graph this function. We have enough information. Let's start by plotting these points that we have found that must be on the graph of our function, and also indicating the horizontal asymptote that lies right on the x-axis at a height of 0. Doing this, we have the following. Notice I've indicated graphically what's happening at all of these points from this analysis above. Now we can take it interval by interval. Consider the first interval from negative infinity up to negative square root of 3. Notice I need to be very close to my asymptote here, rising, right, above the x-axis, and doing so in a concave up way. Well, if I draw that, I have something like this. And then in between negative root 3 and negative 1, well, let's see, that's about here. We need to be concave down, still on the rise, still above the x-axis, finally ending up here where we level off to a horizontal tangent. So drawing that in, we have something like this. And then between negative 1 and the origin, we are still above the x-axis, but now we are decreasing, and we are doing so in a concave down way again. So drawing that in and knowing that we have to end up right here at the origin, we have, then from this point of inflection at 0, we need to travel to this point where x equals 1. We need to do so in a concave up way. We need to continue to decrease, however, and now we're going to be below the x-axis. So drawing that in, we have something like this, again keeping in mind that right here we level off to a horizontal tangent. Then from 1 to square root of 3, well, we're in this interval, so we're still concave up. We are now on the rise. We stay below the x-axis the entire time, and of course we end up at this point. So drawing that in, and finally, from square root of 3 onward out to infinity, notice we are now concave down. We're still on the rise, and we must stay below the x-axis. Again, ultimately ending up very close to this asymptote. So drawing that, we have the following. That is a good graph of this function. Just as one additional note, notice once we have something like this graphed, it's very easy to identify both the domain and range directly from the graph. The domain, of course, since this denominator can never be 0, is certainly all reals. The range, however, we need to look at the graph. It looks like we're hitting all heights from negative 1 up to positive 1. And so that's our range. It wasn't asked for in the problem, but it's a nice thing to add. That's it. I hope that helped.